Okay, so I'm going to talk today about the joint work with Gilad Stern and Aviv Zohar, both from Hebrew University. You heard from Gilad before. And we're talking about efficient multidimensional approximate consensus. So let me first say what this even means. Okay, so a multidimensional Byzantine approximate agreement protocol receives, so there are n players. Each one starts off with some opinion, which is a vector in RD. And the goal is that the players keep sending each other messages, which are their votes, and ultimately everybody should decide on a d-dimensional vector that they agree on, and all of the votes, if it weren't approximate, everybody should agree on a single vector, and all vectors should be inside the convex hull of the good players, the non-faulty players to begin with. And the approximate part is that you don't have to agree on one single vector or a single point in RD. You can agree up to some small epsilon, which is a parameter of the protocol. Okay, I hope this is clear. So let's see an example, if it weren't. So let's assume that blue points are non-faulty players and red points are maybe faulty players. So we should decide on some point in the convex hull of the blue points. And any point will do, and the agreement has to be up to some epsilon around this blue point. So, okay, so previous work has solved this. Abraham et al. Solved this for d equals 1, which is just the one-dimensional case, so you have points on a line. And they solved it up to a third faulty nodes, and it's a polytime algorithm. And for d greater or equal to 2, the best known solutions are exponential time, and the max resilience is it decreases with the dimension. So the higher dimension we work in, the worse resilient we get, and this is a lower bound. So this is kind of not encouraging. So we looked at this problem, and we changed the setting slightly to the validated setting, which we've heard about today twice, I think, which means that there's an external validation function, which just means that when the players initially cast their initial vote, then the votes are, like, some black box procedure checks that these votes are legal, and from now on, everybody plays. So this is like a natural setting. In blockchains, we have this, so we believe a block is legal by some external validation function, which is cryptographic and proof of work. And with this assumption, we can find a solution which is polytime computation per round, and the logarithmic number of rounds, and resilient up to a third faulty nodes, which is much, much better than something that grows with the dimension. So this does not depend on the dimension. Okay, so let me tell you a little bit about how this works. So the setting is that every player waits to get the votes of other players. When it gets n minus t, where t is the number of faulty players, it starts recalculating its own vote, and when it calculates its own vote, it sends it to everybody else. And the calculation is done through a procedure which we call survive k, which means if I am a player in the game, I wait to see enough votes, then I remove outliers in pairs, which means I find the max distance pair and remove it, and I do this over and over and over again until I'm left with at most k points. And once this happens, I vote for the middle point, the middle point between the max distance points that remain. So if this is the set of votes that I see at some time, I'm looking at the set, and I start removing outliers in pairs, so I find the max distance pair. And I keep doing this until I am left with, in this example, 6 points. And once this happens, I look for the max distance pair again, and I vote for the middle between these 2 points, the average. Okay, I hope this is clear. Okay, so this is a simple procedure, and it turns out this is good enough. So this is the vote. And so some properties of this voting procedure, which kind of look trivial, but were not trivial to prove. If I have two players and they have two sets of votes, and the sets of votes have a large intersection or a small symmetric difference, and we set k to be large enough, then we have that if both of the players run this procedure independently and cast their vote, then first of all, the surviving sets will be, their intersection will be non-empty, and points in the intersection will be close to each other. We will talk about this, and every point in the surviving set is close up to every other point. The vote is close to every other point in the surviving set, up to a factor of square root of 3/4 of the initial diameter of the surviving set. Okay, so the proof is very simple. It's a very, very simple and geometric primitive with the medians. So you take, maybe I'll do this slower. So we have this triangle would be y and y tag would be the max distance points in our surviving set, and x would be some point, and the PA would be the vote. I don't know why I called it PA. So we want to see what is the maximum distance between x and the vote. And using just like basic high school geometry, we get that it can't exceed 3/4 of the maximal distance, which is the distance between y and y tag. Okay. So let's see what happens for two players, because we saw what happens with one player. Let's see what happens with two players that might have a small difference between their initial votes that they see. So blue runs survive. The purple points are just points in common between the red and blue players. So blue runs survives, eliminates points in pairs until 6 points are left, and votes. And red does the same, but the points eliminated are different. So there's a priori no reason that they would have the same point. So these are two different votes, and what we want to show is that these votes are close to each other in every round, and the distance converges, the points converge towards each other for every pair and for everyone altogether. So this turns out to be true. I won't go into the proof of why this is true, but because we have an empty intersection between the surviving sets at all times, and because we have that the vote of each player is close to every point in the surviving set, and using the same geometric primitive, the Polonius Theorem, we have that the votes of every two players are close to each other up to a factor of square root of 12/13 r, when r is the diameter of the union of all of the convex hull of the union of all of the surviving sets. So I have a picture because this is a lot. So if the gray area is all of history, and the different colors represent different players and what they see now, we want that when they vote within their surviving sets, the points are close to each other, and this external black ring shrinks over time. So if we look after everybody casts another vote, we would want this black line to move towards like a single point, or epsilon small ball. Okay, so I hope this clarifies anything. So why are we talking about this with regards to blockchains? So I assume that everybody in this room knows about blockchains and DAG protocols. So whenever we talk about the DAG protocol, there are blocks coming in at any given time. And as opposed to maybe just like the basic chain protocol where there is some order, very strict order, and we can decide just use the longest chain rule. With DAG protocols, we have to have some richer voting rule about which block we accept and which block we reject. But this is always true. Like, we always have to, if we have 2 blocks and they have conflicting transactions, like a double spend, we have to accept one block and reject the other. And we can think for a long time that there's only one spend, and then a double spend would come and connect to the DAG somewhere from any direction, and we would have to reconcile this and decide on a single block. So we claim that we can use this multidimensional approximate agreement to not have to reject one of the blocks. So we can have a different voting rule about the transaction, that instead of saying this block is valid and this one is invalid, we can have a different voting rule that each player in the system would use, and we can accept some convex combination of conflicting transactions. So in this case, we think about a transaction as so if I have one coin and I try to send it to spend it to 2 different people, then these would be 2 unit vectors in R2, and deciding on a convex combination would be maybe splitting the money between the 2 players. And this can work also for if I spend the same coin to many players, then we would decide that somehow this money can be split between everyone. But the important thing is that the money is not printed in this way. So everything is inside the convex hull. So even if someone locally might lose money, then the money is not created out of thin air, even if we don't disregard any of the block. So it turns out that you don't actually have to split the money between the users if you do this properly. You can have that with very overwhelming probability. You can, if you wait the wait period, then either you wait and you see that your transaction is approved and you will not lose money, or if someone tried to double spend you, you would know it quickly, and maybe the attacker would lose money, but you would not pay or give what you wanted to give in return for the money. And again, very quickly, because I don't think I have a lot of time. So every block votes about every transaction. I have a figure. So we have some transaction. It lives inside the block DAG, and everybody thinks this is the only spend to some coin. And now, maybe after a while, some conflicting transaction arises in some other block and connects somewhere in the DAG. And now everybody needs to start voting about this transaction, which is a conflict. And we have some voting rule, which I can't go into now, but it turns out that we can use our multidimensional approximate agreement algorithm to resolve this, and so no money is printed, and with high probability, no one loses money. And this is resilient up to a third bad players. Okay, so there are questions about where you should, when is it in, because we agree up to some small epsilon. There's a question of what epsilon is small enough when you're talking about money, because you don't want coins, like small differences to accumulate over time. There's a question of whether this only works for money or can be extended somehow to smart contracts or zero knowledge somehow, and that's it. So thank you.
So the rate of convergence, do you have any thoughts about how optimal or not it is?
Okay, so this is a good question. So square root 12 over 13 is not that great, but in practice it's supposed to converge much quicker, like everything we've looked at is. But it's a good question. Oops.
So maybe I didn't completely understand how this relates to DAG-based blockchain. So the idea is that the blockchain has full agreement, not approximate agreement. But when you compute your own view, you might be in approximate agreement, and so you're guaranteed that you won't lose more than epsilon. That's the.
So what you agreed, so you have two different players in the system, and they have two different DAGs maybe, but not too different. And each computes their vote, and the votes are close up to epsilon. So if you set your epsilon to be so small that maybe it's much smaller than the smallest unit of currency, then you actually would have agreement.